Hi everyone. Before I start solving this paper, make sure that you go to my post tab on my channel page and check out the latest post. There is a form over there for you to fill up if you're interested, like in my tutoring services for A-level maths or further maths. If you know anyone who needs them, please feel free to share the link with them. And in this video, we'll be solving 923 for the maths, A-level for the maths, 9231, paper 44, for the probability and statistics, region 2025. So this paper is an hour and 30 minutes, so let's head on to the first question and finish within the time. Okay, so for the first question, we are told that a random sample of 12 observations of a normal random variable are taken. So normal random variable. So this is an assumption, right? Okay, and then the results give unbiased estimates for the population mean and variance as 10.24. So this is the unbiased mean, the sample mean, and 0.52, that's the unbiased sample variance estimate, 0.52 respectively. So the question tells us to test at the 10% significance level the null hypothesis that the population mean is 10.6 against the alternative hypothesis that the population mean is less than 10.6. Okay, so since our sample size is pretty small, like 12, we're going to use the t-test in here, not the z-test. Okay, so first step is to define our null and alternative hypothesis. So H naught, it states that population mean, let's call it mu, is equals to 10.6, and alternative hypothesis states is less than 10.6. So since we're only focusing on the lower end of the tail, like around this region and not this region, this is only a one-tailed test. Okay, so it's a one-tailed test. All right. Now, now that we know what test we have to do, now we can find our test statistic. So the formula for our test statistic T is equal to the mean, the sample mean minus the population mean that we have defined in our null hypothesis divided by the standard error, which is just the square root. Wait, sorry, let me do that again. Which is the square root of the sample variance divided by the population. So n in this case is 12. So let's substitute everything. So x bar is 10.24 minus 10.6 over sample variance is 0.52 over 12. Yeah, so as you can see, we're definitely going to get a negative value. Okay, but no worries, still doable. 10.24 minus 10.6 over the square root of 0.52 over 12. Okay, so I'm just gonna round it up to 3SF. So it's minus 1.73 to 3SF. All right. Okay, now we are going to take our critical value as this value. So this value is going to be negative. And if our critical value is negative, if our test statistic is less than this critical value right here, this is the region where we have to reject our null hypothesis. All right, so let's find our variance. I mean, our critical value. So to find the critical value for a t-test, we have to know two parameters. First one is the degrees of freedom. So that one is just the number of observations, or like the population size minus one. So in this case, V is 11, and our p-value, which is given by the significance level. So since this is a one-tailed test, like I mentioned earlier, um, you just have to take 100% minus 10%, you'll get 90%. So P is 0.9. Okay, so let's take a look for 11 and 0.9. Okay, so not here. Yep, this is the T distribution table. So 0.9 is 0.9 is here, and 11 is here. So yep, this is our critical value, minus 1.363. So minus 1.363. All right, so as you can see, our test statistic is way less than our critical value. Let me just label it here. Okay, so we can say that since negative 1.73 is less than minus 1.363, do not reject H1. Do not reject the alternative hypothesis. So this means that there is a slight chance that the alternative hypothesis could be correct. Okay, so all right. So our conclusion we can write as sufficient evidence to suggest. And you should always write in the context of the question. Like, so you cannot, you have to be really specific with your conclusion, okay? To suggest that the population mean is less than 10.6. Yeah. All right. So yeah, we can stop here for this question. So yeah, this would be our final answer for this first question. Let's head on to the next question. Okay, so for this question, we are told that the level of sound produced by a particular type of machine was measured for a random sample of 11 such machines. The result in suitable units are shown as below. Yeah, so here you can see we have all the individual sound levels produced by each machine. So using this, for the first part, they're telling us to use the Wilcoxon sign rank test. So it's a non-parametric test. Our only parameter would be the median to test whether the average sound level, so the median sound level in this case, produced by this type of machine is more than 8.00 meters. And they told us is a 5% significance level. Okay, so just like with any other hypothesis test, let's first define our null and alternative hypothesis. So null hypothesis for Wilcoxon tests, instead of using mu, it's better to use m for median. So in this case, m would be equals to 8.00, and then h naught would be the one that the question told us to test. So in this case, it's going to be m is more than 8.00. And since we are only focusing on the upper tail of the distribution, this is only a one-tailed test, not a two-tailed test. Okay, right. So now we can do the real stuff. Okay, so to do the Wilcoxon sign rank test, always draw a table and then label the columns minus, plus, and minus. All right. So this is where you'll be putting the ranks. All right. Okay. So what do we do? Okay. We okay. How about this? Let's take the okay. Let's just label each machine. All right. So um, let's write down the differences instead. Okay. So what's the lowest? 7.6 is so far 8 point. Okay. Yeah, A has the lowest um one, so 7.66. This is definitely negative. Okay, you know what? Let's find the difference first. Okay, and then we rank. All right, so let's first do it for the negatives. So um let's do for the lowest. So 8.00 minus 7.66. This is minus 0.34. So anything that's less than 8 is going to get a negative difference. So that's the convention that we'll be using. Okay, and then what we have the next biggest value. Oh, okay, 7.77. So that's also a negative. So this is minus 0.23. Okay, and then we have 7.92. That is minus 0.08. And then we have minus 7.98. That is minus 0.02. Okay. Now let's look for the closest value. Yeah, I can see it is E, just 0.01. Then the next one is 0.3. That is just two more, so 0.03. And then we have 0.11. That is just 0.11, 8.11. And this is 0.16. Okay, and then 0.21, 0.25. And then finally, this one is just 0.48. Okay, so now let's rank these in terms of magnitude. So the lowest one is 0.01. So 0.01, that would get the first rank. Do we have negative 0.02? We do, yes. So this one, negative 0.02. This would get this rank, okay. Then 0.3, so 0.03. That will get rank number 3. Uh, okay, let's see. Hmm, negative 0.8. Negative 0.08. Okay, let me check one more time. Yep, that's the next one. So this one will be number 4. Uh, 0.09, no. 0.01, no. Okay, 0.11, yes. So this one is number 5. 0.1 something. Okay, 0.16. Yeah, so this one is number 6. 0.16, 0.25, 0.21, wait, 0.16, 0.21, right, 0.21, that is 7, and then minus 0.23, that is 8, and then 0.25, that is 9, mm, negative 0.34, 0.34, that is 10, and then finally 0.48 is 11. Yeah, so as you can see, our highest ranking, like the highest rank number is 11. So yeah, this should be the highest rank number because we have 11. The population size, the sample size is 11. Okay, so now we have to find what P is, like the positive differences, like the sum of the positive ranks. So that is 1 plus 3 plus 5 plus 6 plus 7 plus 9 plus 11. Oh, and by the way, if you actually like forget what you have to find for the Wilcoxon test, it's all given in the formula list. Yeah, so yeah, for the sign rank test, you have to find your P, which is sum of the ranks corresponding to positive. Q is for the negative differences. And then T is the test to distinguish the smaller of P and Q. All right, so let's calculate. So P is 42, and then Q would be 2 plus 4 plus 8 plus 10. So this would be 2 plus 4 plus 8 plus 10. That's 24. And therefore, our T is equals to 24. This is our test statistic. Now we're going to find our critical value. So to find it, it's very easy. You first have to determine whether it's a one-tail or two-tail test. So for our case, it's a one-tail test. I said the explanation earlier, and our significance level is 5%. Okay, so 5% one-tailed, yep, right here. And then our n is, yeah, the size n, so n is 11. Okay, so our critical value is 13. Yeah, so as you can see, our test statistic is more than our critical value. So we are not going to reject H naught. It's opposite from the from the Z and T tests or the chi-square test. Yeah, this because it's a non-parametric test. Okay, so since 24 is more than 13, do not reject H naught. So don't reject a null hypothesis. So that means there is a chance that the null hypothesis could be correct. So you can say, according to the context of the question, it tells you to test whether the level is more than 8. So since our null hypothesis could be correct, it says that sound level is 8. So we can say that insufficient evidence to suggest that evidence to suggest that the average sound level is more than 8. Okay. Yeah. Yeah. So so this is a final answer. And with that, we can head on to the next part. Okay, so for this second part, we have to give a reason why a Wilcoxon sign rank test may be more appropriate than a t-test. So for a t-test to be valid, you have to assume that the population differences are normally distributed, but for Wilcoxon sign rank, we don't have to assume that the population differences or like the population in general doesn't follow any distribution. So we can say that um, the population differences are not normally distributed. Population here is a keyword, by the way, so should always use this word in your um, your hypothesis testing for all types of hypothesis testing. Okay, yeah, so this would be a final answer for this part. Let's head on to the next question. Okay, so for this question, they are telling us that a shop selling electrical goods has three salespeople. Gabriel, Ben, and Charlie. The manager wishes to investigate whether the salespeople are equally successful at selling particular types of items. So the following table gives a record of a random sample of 250 sales in laptops, cameras, and TVs with the numbers sold by each of the three salespeople. Okay, so we have to test at the 10% significance level whether there is independence between the type of item sold and the sales person. Okay, so all right. So to do this type of test, this is called the association test. You have to use the chi-square distribution, like yeah, the chi-square test. So first off, let's also draw this table with the expected frequencies. Okay, so laptop, camera. So yeah, let me just tell A, B, C. And then obviously don't forget your total columns. Yeah, so first step for any chi-square test, you're supposed to find the expected frequency, right? So to find the expected frequency for each of the cells, you take the total of the cell. So let's say I want to find it for this cell. So you take the total of this row and as well as this row, as well as the overall like total, the random sample, 250. Now you multiply 755 and 95. 75 times 95 and divide it by the total sample, which is 250. Yeah, so the expected frequency is 28.5. Now let's do it for camera. So 110 times 95 over 250. So 110 times 95 over 250. You get 41.8. For TV, Avril, 65 times 95. 65 times 95 divided by 250. You get 24.7. Okay, so now let's also do for the remaining rows. So 75 times 97 divided by 250 is 29.1. And then 110 times 97 divided by 250, you get 42.68. And then 65 times 97 divided by 250 divided by 250, you get 25.22. Okay, and the next one is 58 times 75 divided by 250. You get 17.4. And then 110 times 58. 110 times 58 divided by 250. You'll get 25.52. And 65 times 58 divided by 250, you'll get 15.08. Yeah, so these are our expected frequencies. Now we are going to find our OI minus EI squared over EI values. So this is like we're gonna find for each individual cell. So let's take the first cell. So observed frequency is 31. So wait, 31 minus 28.5 squared over 28.5. I'm just gonna write in fraction. So 25 over 114. And the next one, observe is 40, and then expect is 41.8. So 40 minus 41.8 divided by 41.8. You would get 88 over 1045. All right. Okay. So wait, oh, we have 9 values in total. All right. So the next one is observe is 24, expected is 24.7. So zero point 0.7 squared over 24.7. You get, sorry, 49 over 2470. All right, and then next one you get observe is 23 and expected is 29.1. So 23 minus 29.1 squared over 29.1. You get 37, 2, 1 over 2, 9, 10. Okay, and then you have observe is 45 and expected is 42.68. So you get 45 minus 42.68 squared over 42.68. Yeah, uh, you get 33.64 over 2.6675. Okay, so we have 4 more values. Okay, so this observed 29 and expected 25.22. So 29 minus 25.22 squared over 25.22. Oh, okay, I got a decimal. Okay, I'm just gonna express it to 5 SF. So 0.56655. All right. Next one you have observed is 21, expected is 17.4. So 21 minus 17.4 squared over 17.4. Then you will get 108 over 145. And then you have observed this 25, expect this 25.52. So difference is minus 5.2 squared over 25.52. You will get 169 over 15950. Finally, you have 12 minus 15.08. 12 minus 15.08 squared over 15.08. Yeah, you'll get 5929 over 9425. Yeah, so this is all our values. Now we'll find the summation of all this. This would be our test statistic. Okay, so you just add these up, use a calculator. 56655 045 plus 1691550 plus 5929.9425. Yeah, so test statistic to 3SF is 3.67. Yeah. Okay. All right. And then now we need to find our critical value. So to do it for the chi-square, we need to know degrees of freedom first. So for this type of chi-square test, to find it, you multiply it by the number of rows and the number of columns. So in this case, rows is 3 and, oh wait, sorry. Okay, multiply by the number of rows minus 1 times the number of columns minus 1. So 3 minus 1 times 3 minus 1, that is equals to 4. So critical value B is equals to 4 and P uh, is this is always a one-tailed test, the chi-square. So it's 100 times 10 minus 10%, you get 9%, so 0.9. Okay, so 4 and 0.9. Okay, so 4, 0.9, okay, 7.779. Okay, so 7.779. Yeah, so as you can see, our test statistic is less than the critical value. So for chi-square, just like the other z-test and t-test, the rejection region is around here. All right. So if your test statistic is more than 7.779, then H naught is rejected. But here, since 3.67 is less than 7.779, do not reject H naught. Oh, oh no, I forgot to. Oh no, okay, that's all right. Wait, let me write down what H naught is. I completely forgot about that. Okay, so for this type of chi-square test, um, you define your H naught as there is independence independence between the type of item sold, and the salesperson. Oh my. Yeah, and then the alternative one is the opposite. There is an association, or it's dependent between the type of item sold and the salesperson. Yeah, sorry for this mistake. Forgot to um, define the null and alternative hypothesis. Yeah, so there is a chance that H naught is correct, right? So I guess we can say that sufficient evidence to suggest, okay, we write it in full, that the type of item sold and the salesperson are independent. Yeah, so this would be a final answer for this question. let's head on to the next question. Okay, so for this question 4, we're told that the continuous random variable x has this PDF f probability density function. So you can see it's given as a piecewise function. So kx is valid for 0 to 1 and kx squared is 1 to 2. So first part, we have to show that k is equal to 6 over 17. Okay, so to do this, we have to use the fact that the area under a PDF, the total area is always equals to 1 because the area of like a PDF from one point to a certain point is just a probability of all the random variables that is covered in the area. So obviously, the probability of all the random variables combined would be equal to 1. So let's do that. So we find the area, find the area under kx first. So okay, the limits will be 1 and 0, kx dx. We add it with kx squared, so 2, 1, kx squared dx goes to 1. So this one will be kx squared over 2, 1, 0 plus kx cubed over 3, 2, 1 goes to 1. So sub 1 first here. So k over 2 minus k times 0 squared, that is 0 over 2, so that's just 0, plus substitute 2, you get k times 2 cubed, that's 8, so 8k over 3, so 8 over 3k minus k times 1 cubed, that is k over 3, yeah, that's equals to 1. Okay, so let's add all these terms up together. So half k plus 8 over 3k minus 1/3 k. You can get 17 over 6k equals to 1. Then you'll get k is equals to 16 over 17. So this would be the answer for our first part. Oh, and don't forget to write shown. Okay, let's head on to the next part. Okay, so here they're telling us to find the cumulative distribution function of x. So the cumulative distribution function of x is the function, like instead of integrating from one random variable to the lower random variable, you can just substitute a random variable into that function and you will get the probability of having a less than or equal to that random variable. Okay. All right, so to find our cumulative distribution function, we take our first piecewise function and we integrate it. But instead of writing k, we write t, or any dummy variable, and then we differentiate it with respect to that new function. And as for the limits, we only take the lower limit, and the upper limit would be replaced by x. So this would just be kt squared over 2 x 0. So there's just kx squared over 2 minus k times 0 squared, that's 0 over 2, so minus 0, yeah. So this is the CDF from 0 to 1. And to find the next CDF, it's slightly different because it includes 1. So you have to substitute a 1 into this function. So it's going to be big F1, right? So that's, well, I forgot we found K already. So 16 over 17 times 2, 1 squared. So this is 1, this is 3, so 3 over 17. So you have to add this up to the integral later. So 3 over 17 plus the integral of same process for this only take the lower limit, the upper limit you replace with x. So this is just kx squared dx. Then you get 3 over 17 plus kx cubed over 3 x1, and you get 3 over 17 plus, we did, oh, sorry, this is t, not k, yeah. So you get kx cubed over 3 minus k times 1 cubed, that is k over 3. So that is 16 over 17 times 3. Yeah. And then you would get 1 over 17 plus kx cubed over 3. Oh my, why am I forgetting to include it? Yes, k is obviously 16 over 17. So this is 1 over 17 plus 2 over 17 x cubed. And then this one is 16 over 17. That is also 3 over 17 x squared. Okay, and now we can write down the cumulative distributive function. So we define it as a big fx. So to start, you should always write down a 0 first. So big fx is 0 when x is outside of this range, so less than 0. So x less than 0, and then the next one is 3 over 17 x squared. That is for x between 0 and 1. Yeah. And then we have 1 over 17 plus 2 over 17 x cubed. That's for x between 1 and 2. And then finally, you write down 1. That's for x more than 2. All right, yeah. So this would be our final answer for this second part of this question. Let's head on to the next part. Okay, so for this third part, we need to find the median value of x. So to find the median value of x, there's two ways. Either you can integrate the PDF. So you take your first piecewise function, you integrate the whole thing. You take the second piecewise function, you integrate with the lower limit, which is 1, and then upper limit is m. And then you equate it to half. So that's one way. Second way is to just take your CDF. Okay, so you take either one of the CDF. I'm going to take this and just equate it to 0.5. And then make x equals to m. So I'm going to do the second way. So 1 over 17 plus 2 over 17 m cubed equals to half. So let's separate the m cubed term. 2 over 17 m cubed, that's equals to half minus 1 over 17. You get 15 over 34. And then m cubed, you get 15 over 34 divided by 2 over 17. You get 15 over 4. And then you take the cube root, 15 over 4, and round it off to 3SF. Or you can just leave it as it is. 15 over 4. I'm going to do both. So to 3SF, you get 1.55. Let's see if it's within our range. Yeah, it's between 1 and 2. Yep. So yeah, this would be our final answer for this part. Let's head on to the last part. Okay, so for the last part, we're told to find E of 1 over x. So we're told to find the expectation of 1 over x, not x. To find the expectation of a continuous random variable, there's a formula given for it in the MF19. Yeah, so yeah, you have it right here. Ex is the integral of x small fx dx. So you have to use your probability density function. And notice, yeah, so let's write that down. So E 1 over x. So we want to find 1 over x, not x. So instead of integrating, instead of multiplying x, we're going to multiply 1 over x times the first function. So it's kx, so that's 16 over 17x, 16 over 17x dx. Don't forget to put your limits. So the range is from 0 to 1. So lower limit is 0, upper limit is 1, plus the second one, which is 1 and 2. So 1 and 2, and then you take x, which is 1 over x times, sorry, you take 1 over x times the PDF from 1 to 2, that's KAX squared, so 16 over 17 x squared dx, so x cancels out, then 16 over 17, you can take it out, and then here you only have to integrate 1 with respect to x. So 1, 0, plus you can also take out 16 over 17 for this, and get 2, 1, x dx. Yeah, so 16 over 17. Integrate 1 with respect to x, you get x, 1, 0, plus 16 over 17. Integrating x, you get x squared over 2, 2, 1. So this one becomes 16 over 17. 1 minus 0, that's 1, plus 16 over 17. 2 squared over 2, that is just 2, minus 1 squared over 2, that is just half. So you can just put all this into your calculator. Get 15 over 17. Okay, all right, let me check if I've done anything wrong. It doesn't seem so. Nope, I've not. Yeah. Hmm. Yeah, I think we can say that this is the final answer for this last part of this question, 15 over 17. So it's the entire question. Let's head on to the next question. Okay, so for this question 5, we are told that Eric has 3 identical coins, each of which is biased. So probability of obtaining a head when it's thrown is 1/3. So each coin, when you throw it up, obtaining a head, the probability is 1/3. Okay, random variable x is the number of heads obtained when Eric throws the 3 coins at the same time. Okay, so for the first part, we need to find the PGF GXT of x. Okay, so to find the PGF, let's first find the values of x. Okay, so x can be either equals to 0, 1, 2, or 3. Yeah, you can get 0 heads, 1 head, 2 heads, or 3 heads. Yeah, so let's find the probability of each one. So px0, that just means all of them are tails, so 1 minus 1/3 cubed. That's equal to 1 minus 1/3 cubed, 8 over 27. And then px equals to 1. That just means only one head. So 1/3 times 1 minus 1/3 squared. Only two coins have tails. So 1/3 times 2/3 squared, you get 4/27. And px equals to 2, you will get 1/3 squared because two heads. Yeah, two heads, and then only one tail, so 1 minus 1/3, multiply by it, times 1/3. Yeah, you get 2/27, and then lastly, probability of x equals to 3. So all three coins have heads. That's just 1/3 cubed, which is 3/27. Oh no, sorry, 1/27. Okay, so to check whether all of our probabilities are correct, just add all of them up. You should get 1. Wait, what? Okay, wait. So number of heads obtained when Eric throws the three coins at the same time. Oh, okay. So for x equals to 1, you can either have head, tail, 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 head, tail, or uh, tail, tail, head. So there's actually three other possibilities. So if you multiply by 3, you would get 4/9. And then for px equals 2, you get one tail, right? So tail, head, 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 tail, head, or head, head, tail. So three possibilities. So it's just 2/9. Okay, let's see whether I can get one. So 1/27. Yep, I got one. So yeah, GXT. You just write down the probability and you multiply with t to the power of the random variable. So this is 8 to the power of 7 times t to the power of 0, then plus 4/9 times t to the power of 1 plus 2/9 times t to the power of 2, t squared, and then finally 1/27 times t to the power of 3. Yeah, so this would be a final answer for this first part. Let's add on to the next part. Okay, so for the second part, we're told that Eric also has two fair six-sided dice with faces numbered from 1 to 6. Random variable y is the number of sixes obtained when Eric throws the two dice at the same time. Okay, so we're also told, okay, we're given the PGF of y, which is 25/36 plus 10/36t plus 1/36t squared. Okay, and then we're also told that Eric throws three coins and the two dice. Random variable z is the sum of the number of heads obtained and the number of sixes obtained. So the z is basically just the sum of x and y. So second part, we need to find the PGF of z, GZT, expressing answer as a polynomial in t. So the whole thing must be expanded. Okay, so since z is just a sum of x plus y, and x and y, they are independent, we can say that GZT is basically the multiple of GXT times GYT. Okay, so GZT, let's write GXT first. So 8/27 plus 4/9t plus 2/9t squared plus 1/27t cubed. and then times GYT, that is 21 over 36 plus 10 over 36t plus 1 over 36t squared. All right, so now let's expand. So let's find the constant first. Just multiply 8 over 27 with 25 over 36. Yeah, you get 50 over 243. Now you find the term in t. So you multiply 8 over 27 with 10 over 36 and 4 over 9 with 25 over 36. Then you would get 95 over 243 t. And then for t squared, multiply 8 over 27 with 1 over 36t squared plus 4 over 19 times 10 over 36t plus 2 over 9t squared times 25 over 36. Then you would get 139,486 t squared. And for t cubed, just multiply 4 over 9 times 1 over 36 plus 2 over 9 times 10 over 36 plus 1 over 27 times 25 over 36. It would get 97 over 972 t cubed. And then that's plus t to the power of 4, 4 over 9, okay, cannot. All right, 2 over 9 t squared times 1 over 36 t squared plus 1 over 27 t cubed times 10 over 36 times t, you get 4 over 2, 4 over 3 t to the power of 4. Finally, t to the power of 5, just multiply 1 over 27 times 1 over 36. You get 1 over 972 t to the power of 5. So to check, again, just add up all the probabilities, see if you get 1. Okay, so give me a while. 243 plus 1 over 972. Yep, I got 1. So yeah, we can say that this is a final answer for the second part. Let's head on to the last part. Okay, so for the last part, we need to use the probability generating function gzt to find the expectation of z and the variance of z. Okay, so to find the expectation, we can use this formula right here. So you can see the expectation of x is just the probability generating function differentiated with t substituted with t equals to 1. And for the variance, it's the second derivative of the PGF with t equals to 1 plus the expectation minus the expectation squared. Okay, all right. So I believe we should differentiate first. Okay, let's just find the expectation first. So g prime zt, to differentiate, constant term goes away. The t term becomes 95 over 243. Then the t squared term, 2 times, okay, wait, 2 times 139 over 486. You get plus 139 over 243 t squared. No, why did I put t squared? Yeah, just t, and then the t cubed term. You just multiply 3 times 97 over 972. 979 97 over 3 to 4 t squared plus t cubed. To find t cubed, just differentiate the t to the power 4 terms, so multiply 4 times 4 over 243, and you get 16 over 243, 16 over 243 t cubed plus this one, t to the power 5, you multiply 5 times 1 over 972, we get 5972 t to the power 4. Yeah, so this is our formula for g prime zt. So g prime z1, this is equal to the expectation of z. Just substitute everything, or just add up the coefficients. That will also do it just fine. It's 97 over 324 plus 16 over 243 plus 5 over 972. You'll get 4 over 3. So this is Ez. Now we have to find the variance of Z. Oh wait, before that, we need to find the second derivative. So second derivative, just differentiate g prime z. This goes away, this just becomes 139 over 243 plus this t squared, just 2. T squared becomes t, so 2 times 97 over 324. You will get 97 over 162 times t plus t cubed becomes t squared, so 3 times 16 over 243. You will get 16 over 81 t squared plus 4 times 5 over 972. Yeah, you'll get 5 over 243 t cubed. Yeah, so now we can find the variance of z. That's just g prime z1. Yeah, z1 plus the expectation minus expectation squared, ez squared. Yeah, so just substitute in, just type into a calculator. 243 plus 97 over 162 plus 16 over 81 plus 5 over 243 would get 25 over 18 plus 4 over 3 minus 4 over 3 squared. So 3 minus 4 over 3 squared, you would get 17 over 18. Yeah, so these two are our final answers for this question. If you want to check whether differentiation is correct, you can just type the original probability generating function of z and then differentiate it and then equate x to 1. Then you'll get your expectation. Do the same for the derivative, the first derivative, you differentiate it, equate x to equals to 1, see if you get 25 over 18. So with that, let's head on to the final question. Okay, so for this question, we're told that Lena and one or two statisticians will write songs. Time of a song is the number of minutes for which it lasts for a random sample of 10 of the songs. Nina calculates a 95% confidence interval for the population mean time, mu minutes. We're also given this confidence interval for mu, 2.95 and 3.13. The times x minutes of Lena's songs are normally distributed. Okay, so for the first part, they're telling us to find sigma x and sigma x squared for the 10 songs. Okay, so to do this question, let's just start off as if we're doing a confidence interval question. Normally, like we just have to like kind of reverse our process, right? All right, so let's find the what you call the p-value first. So for this, you find alpha over 2. It's a two-tailed test. So you'll get 0.975. And yeah, to get the confidence interval formula, we take our t formula, the test statistic formula. We're using the t-test because the sample size is pretty small. So t is x bar minus mu over variant over the standard error, which is the variance over the size square rooted. So let's rearrange from mu. So you get t sigma t times s squared over n square rooted. That's equals to x bar minus mu, and then mu you will get x bar plus minus t times s squared over n. All right. So let's form the equation now. All right. So let's take the lower limit. So 2.95 is equals to x bar minus t s squared over n. Excuse me. Goes to 1. And then upper limit 3.13 is x bar plus t times square root s squared over n. This is equation number 2. All right, so you just add up equation 1 and equation 2. You'll get 2x bar close to 2.95 plus 3.13, and then x bar would be 3.04. So from this, we can easily find our sigma x, because we know x bar is sigma x over n. So 3.04 times 10, you get 30.4. Yeah, so this is our answer for sigma x. Now let's find the sigma square, say sigma x squared. Okay, so to find it, we're going to subtract equations 1 and 2. Then you would get 2t times square root of s squared over n. That is, wait, yeah, that's equals to 3.13 minus 2.95. And then you would get s squared over n. That's equals to 3.13 minus 2.95, 9 over 50 times 2 times t. So to find the value of t, we need to know the degrees of freedom. So in this case, it's 9, as well as the p-value, which is 0.975. So I actually have it right here, 2.262. So t is equals to 2.262. 2.262. Wait, 2.262. Okay, let's remove the square root and just square this whole thing. So 9 over 50 times 2 times 2.262 squared. Get 225 over 142,129, and s squared is just 1 minus n9. So 1 over n minus 1, that is 9. Sigma x squared minus 30.4 squared over 10. Yep. Yeah. Okay, and that is equals to this thing times n. So times 10. Okay, that's 2250 over 142,129. Okay, so after like a lot of solving, I'm not going to do the solving here, right? So times 9 plus 30.4 squared over 10, you would get 92.623 SF. Yeah, so these are our final values for sigma x and sigma x squared. Let's head on to the last part. Okay, so for this last part, we're told that Mona songs have times y minutes that are normally distributed. The times for the random sample of 8 of Mona songs are summarized as follows. So sigma y is 24.8 and sigma y squared is 76.98. And then we're told Mona claims that the population mean time of her songs, we're going to call it mu y, greater than the population mean time of Lena's songs. So Lena is mu x. Okay. Okay, and then they told us assuming that the two distributions have the same population variance. So here they're really cementing the fact that you have to use the t distribution. We have to test at the 5% significance level whether there's evidence to support Mona's claim. Yeah, so this is the t-test for the difference in population means. Okay, so first step is to define our null and alternative hypothesis. So null hypothesis would be that mu y is equal to mu x. In other words, mu y minus mu x is equals to 0. And then the alternative hypothesis is the one that we're testing, whether mu y is greater than mu x. So in other words, mu y minus mu x is greater than 0. And again, since we're only interested in the upper tail of the distribution, this is a one-tailed test. Okay, so now we have to find our test statistic. So test statistic, the formula is almost similar. It's the differences in the sample mean. So y bar minus x bar, and then minus the population mean, mu y minus mu x over the standard error, which is the combined population sample variance over the total size. Okay. All right. So let's find everything that we need to. So y bar minus x bar. So y bar is 24.8 over 8. Yeah, that's 8. Then minus x bar is 3.04. 3.04. You get 0.06. Okay. Now let's find the combined population variance. So they told us to assume they have the same population variance. So we're going to use this formula. Okay. Yeah, so as you can see, this formula isn't suitable, so we kind of have to rewrite it. Okay. So yeah, so this is going to be, okay, it's a plus sign, so it doesn't matter. So y minus y bar squared plus x minus x bar squared over ny plus nx minus 2. Yeah, let's split up the fraction. So y minus y bar squared over ny plus nx, so over 2 plus sigma x minus x bar squared over ny plus nx minus 2. Okay, so to re-express this, we're going to take reference from here. So you can see that this is just the same as 1 over ny plus nx. So ny is 8, nx is 10 minus 2, that's 16. And then this numerator is just equals to y sigma y squared minus sigma y whole thing squared over n. So n is the population size of y. I mean, the sample size of y, that's 8 plus 1 over 16. This is the same for this. Sigma x squared, that's 92.6 minus 30.4 squared over 10, right? Over 10, and then this would be equal to 1 over 16 sigma y squared, that is 76.98 minus sigma y whole thing squared, that's 24.8 squared over 8 plus 1 over 1 over 16 times 92.6 minus 30.4 squared over 10. Yeah, this is 23 over 2000. And this whole thing is equal to 76.98 minus 24.8 squared over 8. You get 71 over 4000. Yeah, so this is our sample variance. Now we can find our test statistic. So 0.06 minus 0 over s squared, that is 71 over 4000 times n. Wait, oh, sorry. Yeah, this is supposed to be s squared plus 1 over nx plus 1 over ny. So 1 over nx, that's 1 over 10 plus 1 over ny, that's 1 over 8. Yep. Okay, that's good. Okay, so just type into calculator. Okay, so 0.06 over 71 over 4000 times 1 over 10 plus 1 over 8. You'll get 0.94923 SF. Okay, yeah, so now we need to find our critical value. So as I said, test is one-tailed. So we can just take 100% minus 5. Will give us 95%. So p-value is 0.95. So 0.95 degree of freedom is this denominator here, 16, and y plus nx minus 2. So 16 and 0.95. Okay, so 16, 0.95, you get 1.746. So critical value 1.746. 1.746. Okay, so you can see clearly that since our test statistic 0.949 is less than 1.746, we do not reject our null hypothesis. So do not reject H naught. Okay, so H naught, so there is a chance for H naught to be correct. So yeah, so it is possible that there's no difference, like the population mean for both for Mona's songs is equal to that of Lina's songs. So we can say that there's insufficient evidence to support Mona's claim. Yeah. So yeah, this is our final answer for this last part of the last question, as well as the entire question. And we have also come to the end of this paper. So I hope you found this video helpful. If you did, please make sure to like and subscribe to this channel for more future past paper solving videos of A-level maths and further maths, as well as topical videos. If you have any queries or doubts or any feedback or um, any future video ideas, whatever it is that you want to know and is relevant, please leave it down in the comment section below. If you Yeah, as I said at the beginning, please go over to the post tab, check out the latest post, and yeah, this is the last video of the Major 2025 series. And with that, I'll see you again next time. Okay, thank you.